Okay, so in this video, I'd like to talk a little bit about the concepts of the unit tangent vector and the curvature of a curve, which are discussed in your textbook. Again, the textbook does a nice job of very clearly explaining how to calculate them, but I think it's a little short on giving some meaning to them. So let's just talk about these things briefly. And I think my main issue with the textbook is that it sort of does them in what I consider the wrong order. Does what I consider the wrong order. So if we have a curve here, and we have a point, and from this point we find a tangent vector, like that, again, this tells us this is the velocity. All right. And the magnitude tells us the speed, and the direction that the arrow points tells us the direction of the velocity, or the direction that the point's moving. That's all well and good, but sometimes we're really not terribly concerned about the speed. We're just concerned about the direction. And in that particular case, then the length of this vector can get in the way. So really all we do to find a tangent vector, a unit tangent vector, so let's say that my unit tangent vector is going to point in the same direction, but it's going to have length 1, and I arbitrarily chose that to be length 1. So how would we find the unit tangent vector? Well, the unit tangent vector t, it's usually called, is just going to be the velocity v of t over the speed, and the speed is just the magnitude of the velocity vector. Okay, so really all we're doing is we're taking some vector, which we know to be a tangent vector, and we're normalizing it, or we're finding the unit tangent vector. Okay, so let's keep that in mind as we go forward here. Okay, now on a related topic, we talked in the last video about the arc length. This is some length, and we usually designate the length of this S. All right, that's the arc length. Now, as I'm traveling along the arc, assuming though, again, we're going to assume basically from now on that the curves don't backtrack, that there's no sort of funny business which would make our arc length calculations more difficult. So we're just going to assume that we can calculate the arc length by integrating the speed over this time, and that, again, like we said in the last video, that makes sense. But what's also true here is that the change in speed the change in arc length with the respect to the change in time, if I take the rate of change of the arc length, right? So in a certain amount dt, I go a little bit ds, right, along the arc, then that rate should give me the speed. And that's, again, something that we've seen, and it makes sense, and this idea fits perfectly with the idea that, well, if we just sort of solve this out like this, we get that, which implies that s is equal to the integral f prime of t dt. Now, there's a little bit of shady business going on here with the variables. I should do a translation of variables, but that's okay. You get the idea. So this idea of the change in arc length over change in time, or the rate of change of the arc length as I move along the curve, it sort of fits with our notion of what we mean is going on here. Okay, so how does this relate to the unit tangent vector? Okay, let's take another example here. So I have a point, or I'm sorry, I have a curve, and I'm going to be moving along the curve at a certain rate. So I want to look at the change in the position vector, right? And I want to compare that with the change in arc length. Okay, so let's take some examples here. So I have a little picture. So let's say I start here at this particular point, and then I move a little bit along the curve, and I change this. So I have a position vector 1. So this would be position vector 1, which, f of t1 maybe, and this one down here is f of t2. So between f1, or so t1 and t2, I moved from here to there. And I can define that change in position vector by another vector, which we will put right there. And this green vector we're going to call delta f of t. So the change in the position vector for a certain change in time. Okay, now on the other hand, the arc length, I moved along the curve. So I moved along the curve in this direction, right? So that length right there we can call delta s. Now what happens as the time increment gets smaller and smaller? But as these two approach each other, in other words, as delta t gets smaller, and as let's do this in green, as delta f over delta s approaches df ds, that is going to, these two quantities are going to be basically the same. Now the other thing we want to talk about is what direction is this going to point? Well, the answer, the direction that this is going to point is, you can see that it's almost already tangent, and as these two, as these points get closer and closer together, right, the vector connecting them gets closer and closer to tangent. So this actually is going to point in the tangent direction. So df is going to df ds is going to point tangent to the curve. But we also know that the change in the position vector and the change in the magnitude of the change in the position vector and the length of the arc, they approach each other, which means that the length of this is going to be 1. So that means that this, the derivative of f with respect to s, is just the unit tangent vector. Okay, again, because we know it's going to point in the tangent direction, and we know it's going to have length 1. It's going to have length 1, again, because this and this, they approach the same thing. So this arc and this arc, as the arc gets smaller, they become, they coincide. And then they points in the tangent direction, because that's sort of this idea of, it's the same secant proof limit of the secant line to get the tangent line. This is sort of a secant line, and as our points get closer and closer, the secant line becomes a better and better approximation of the tangent line until eventually it is the tangent line. So that gives us a little bit of intuition as to why the book went to trouble. I'm pointing this out because the book went to trouble to tell you that df ds is t. And as a matter of fact, in the book they wrote it, they called the position vector r. I've been using f. It doesn't matter. They call dr ds equal to t. And I just wanted to give you a little bit of intuition as to why that happens. Okay, the last thing I want to talk about in this video is dt ds. And dt ds is important in the textbook because it turns out to be normal to the curve. And it's actually how we go about finding our curvature. Okay, so let's talk about why. I think it's not so obvious as to why dTds is normal. They do a little argument in terms of dot products, and that's a fine argument. It's algebraic, it's nice, but it doesn't give you, again, doesn't give you a whole lot of intuition. So let's take an example. And we're going to do a simplified example, but the simplified example can easily be extended to more complicated problems. Okay, so we're gonna start on we're gonna start on a unit circle. Okay, if this doesn't appear circular, I apologize. It's just because of screen resolution issues. It's meant to be a unit circle. So on a unit circle, or not a unit circle, just a circle. This is a circle of radius r, and I'm going to move along the curve. I'm going to move from this first point to this second point here. Okay, and we want to see what happens. To the unit vector. So the first thing I want to do is I want to put in my unit tangent vectors at each point. So here I have a unit tangent vector at this point. All right, and then now I'm just telling you that these are unit tangent vectors. They are. So we're just saying that that's a unit. So here I have a unit tangent vector there, and I have a unit tangent vector at the end point. And the question is, how does the unit tangent vector change as I move along the arc? So this is this little change here. is you can call it delta s, right? I moved along the arc. So we want to know what's the change in the tangent vector with respect. Well, actually, I'm doing in terms of deltas. What's the change in what's the change in the tangent vector with respect to the change in arc length? Okay. So I'm going to take another copy of my unit tangent vector. I'm going to put it right here, just so we can see how it changes. So remember, because we can move vectors around. So this red vector right here, which points from the first one to the second one, that represents dt delta t delta. That represents delta t. Okay, so the question is, what direction does dt ds, and delta s is just a scalar, so multiplying by delta s doesn't change the direction of dt. So if I can figure out the direction of delta t, then I can figure out the direction of delta t delta s, or dt ds. Now you can already sort of see that this is sort of pointing inside the circle. It's pointing sort of in this direction towards the center of the circle. Now exactly what direction is that? Well, let's take a second to think. So the thing to notice is that this right here is a right angle, and this is a right angle, and that's because these are tangent vectors. That means that they're perpendicular to these radii for a circle. Now you can make sort of a similar argument. You have to change the argument a little bit if it's not a circular orbit, but that's okay. We can just trust me that you can extend this argument. Okay, so we have those two things. So from that and a little bit of geometry, we can see here that this vector, this angle and this angle are the same, which means that this triangle here and this triangle here are similar. Okay, so and we also know that they're sort of translated or rotated by 90 degrees. So if we look at, we can see that this dt, the direction of dt, is going to be perpendicular to the direction of ds. As R1, as position 1 and position 2, as they get closer together, so as I move along the curve here, then delta s becomes closer and closer to tangent, or ds becomes closer and closer to along the tangent line, or being linear to the tangent line, which means that delta t is going to be closer and closer to perpendicular to that. So we can see that as the direction of these things, as my points get closer and closer together, this vector delta t is going to point in towards the center of the circle. Thus, that means that delta t, in the limit, we get dt ds, and that's going to be perpendicular to t.